Hello and welcome. In today's video, we're going to be going over topic 4.3, what the derivatives will tell us about the graph, or really what is the derivative going to tell us about a function. To start out, I want us to find the first and second derivatives of the following. Just walk us through the process, as we're going to be using that a lot in today's video. So for the first derivative, we're just going to use the power rule for this first one, and we're going to get 6x minus 6x squared. And then for f double prime of x, it's going to be the exact same, other than it's going to be minus 12, or take the power rule, really. That's what I mean by it being the exact same. For this next function, this is going to be a product rule, so we get the derivative of the first, which is 2x, times by the second, which is sine of x, plus the first times by the derivative of the second. Alrighty, for the second derivative, we have to take the derivative of the first, so we get, and interestingly enough, I'm just going to take a moment here. This is now going to be two product rules we have to do. So the derivative of the first is 2 sine of x, plus the first times by the derivative of the second, which is cosine of x. Alright, now we have to do the second derivative, or the second derivative here. So we get the derivative of the first, which is 2x, times by the second, which is cosine of x. Alright, then plus x squared times by the derivative of the second, which is going to be negative sine of x. Now all we have to do is simplify this a little, and we get the answer of negative x squared sine of x plus 2 sine of x, and then plus 4x cosine of x. And that would be our answer. So let's get into this. So we need to first build some tools here. The increasing or decreasing test. So we want to use f prime to tell us if a function is increasing on an interval. So if f prime of x is greater than 0 on an interval, then f is increasing on that interval. If f prime is less than 0 on an interval, then f is decreasing on that interval. So find the interval. So we want to now use that to find the intervals where f is increasing or decreasing. So we need to first find this function's derivative. Alright, so we get f prime of x is equal to 4x cubed minus 4x plus 3. Then what we're going to do is we are going to not take the second derivative, but we're going to factor out, that shouldn't have been a plus 3. But we're going to factor out a 4x, and that's going to leave us with an x squared minus 1, which is going to give us 4x, x plus 1, and then x minus 1. Now you may remember from our last video that anywhere where f prime is equal to 0, that is a critical point. So what we're going to do, or possible places where there's maximums and minimums, but I'm kind of getting ahead of myself here, but we're going to use these zeros to tell us a bit more information about the graph. So negative 1, 0, and 1. So all we have right now is this number line. Now we're going to plug in values in this number line to determine if f is positive or negative in between these values. So if we plug in a value, let's say negative 100, into the function f prime, you will see that this first, or that negative 4x is going to be negative, x plus 1 is going to be negative, and then x minus 1 is going to also be negative. because this is a negative times by a negative by a negative, this is going to be negative, or f is decreasing. Next, from negative 1 to 0, we're now going to plug 1/2 into this. Well, or sorry, negative 1/2. This for x is going to be, this is going to become negative 2. This is going to be positive 1/2, and this is going to be negative 3/2. So we see that this is going to be a negative times by a positive times by a negative, or it's going to be positive or increasing. F prime is going to be positive or increasing on that interval. From 0 to 1, so we're going to plug in like 1/2 or any number in between them. You're going to see that we're going to get 2 times by 3/2 times by negative 1/2. So this is a positive times by a positive times by a negative. So f prime is negative. Alright. And then finally, if we plug in a really big number like 100 into this function, we get a positive times by a positive times by a positive, or the function is positive from 1 to infinity. So now we can see where f is positive or negative. We can now know where f is increasing or decreasing. So what we'll see here is that f prime, or sorry, not f prime, but f is increasing where f is increasing where f prime is positive. So f is increasing in this case from, and we're going to include the endpoints, negative 1 to 0, and then 1 to infinity. Alright. So then we have f is decreasing where f prime is negative. Since we know f prime is negative from negative infinity to negative 1, we can't include infinity, so I accidentally did include that infinity up there. So we know that f prime is negative, so f is going to be decreasing from negative infinity to negative 1. And then we know it's going to be decreasing from 0 to 1. Alright. So now that we have this in our toolbox, and that I've brought up critical values, let's refresh ourselves a little more on relative min and maxes, which are just points where they are greater than all other values around them. Well, the derivative gives us a way to test for this. You may recall that there's a possibility of a relative maximum or a relative minimum happening where f prime is 0. Well, we can tell with the derivative where the derivative will be 0, but not only that, where it's increasing and where it's decreasing. So, suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative, which is going to look like this, at c, then f has a local maximum at c. So you might notice that, well, it's increasing, but then it starts to decrease. So no values are ever going to be greater than c around c, or near c. Alright. If f prime changes from negative to positive at c, then f has a local minimum at c. So it's going from decreasing. Sorry, I didn't want that to convert. So it goes from decreasing, and then it starts to increase. Alright. If f prime does not change sign at c, then it is a shelf point. So really what this means is that there's going to be a point where it's 0, and we see the function still goes back to increasing. Think of this as like x cubed. Alright. So now we're going to use this info to determine the local extrema of the following. So we need to start by taking the derivative of this, and I'm actually going to change my color, make it less pink. Alright, d over dx. So we get dy dx is equal to 3x squared minus minus 12x. Alright, now what we're going to do is we're going to factor out a 3 from this, a 3x, and then also factor out, or not factor out, but then multiply that by x minus 4, and we can see this in factored form. And now we have intervals here, so we're going to plot them on the number line like we did up here. This number line gives us a lot of useful information. So we know that x is going to be equal to 4 and x is equal to 0 as our two possible critical numbers. So we're going to plug in a number less than 0. Let's say -1. If we plug in -1, this 3 is going to be negative, and this x minus 4 is going to be negative. A negative times by a negative is a positive, so it's increasing. Then from 0 to 4, well, we're going to plug in a value like 1. The outside's positive, but the inside is negative, so it's going to be decreasing. Finally, once we hit 4 or greater, let's say plug in 5, the outside's going to be positive, and the inside's also going to be positive. So a positive times by a positive is a positive. Well, we have a critical number here at 0. So if f changes from positive to negative at C, then f has a local maximum. So we know that there's a local max at x is equal to 0, and we'll have to plug this into our original function. It looks like that will be -135. So 0, -135. Whenever you're giving local maximums, remember that you have to give the point. If you're giving absolute maximums or global maximums, you have to give the y value. Then now, if we look at this other critical point, 4, we see it goes from decreasing to increasing, or f prime goes from negative to positive at x is equal to 4, so that there must be a minimum at x is equal to 4. So there must be a local min at x is equal, at 4. And then now we have to plug in a value, or plug in 4 into our original function. 4 cubed is 64. Give me one moment to compute the math on that. And we get a value of -167. Alright. And now we found our local min and our local maxes. But as you've also noticed, we can also determine the intervals where f is increasing or decreasing. So this number line that we have here is actually really useful. And we're going to keep using it. Well, until you want to just do it in your head, then you can stop using it. But that's just a little tip I like to use for when I'm doing it. That way I can keep track of it on my paper. Right. So, we've been using a lot of the first derivative, but what does the second derivative say about f? Or the function f, rather. Well, if the graph f lies above all of its tangents on an interval, then, or on a interval I, then f is called concave upward, or on I. If the graph f lies below all of its tangent lines, then it is concave downward on I, denoted as either f concave up or f concave down. So, now we're going to use this, and we actually have a little test to tell us if a function is concave up or concave down. And it's called this concavity test. So it goes A, if f double prime is greater than 0 on an interval I, then the graph f is concave up on I. If f double prime is less than 0 on an interval I, then the graph f is concave down on I. So, inflection points. So, an inflection point is a point on the curve y is equal to f of x that changes from positive to negative. So, we really want, whenever we're looking for possible inflection points, also denoted as pips. Possible inflection points. We want to be knowing where f double prime is equal to 0, as that's going to tell us where it might be possibly changing to positive or negative. But we also want to know where f double prime is undefined, as that can also be another point where it can change its concavity. Alright, so we want to find all the inflection points and intervals where f is concave up and or concave down for the following. So, f prime of x, we're going to start there, is equal to, well, the derivative of 1 is 0 plus 6x minus 6x squared. Alright. Then we have to go to f double prime of x, and we get 6 minus 12x, or just 6 minus 12x, sorry. Now all we have to do is solve this for 0, so we get 0 is equal to 6 minus 12x. Then we get, negative 6 is equal to negative 12x. Or x is equal to 1/2. Alright, we're going to use a number line again. This time we're going to denote it as f double prime. And really, this is just a one-dimensional graph, I want to say, but in all honesty, that would also kind of be in some ways wrong, so sorry if that confuses you in any way. So we're going to plug in 1/2 here on the graph. So if we look at f double prime and we plug in a value less than 1/2, well, let's say we plug in a value of 0. Let's plug in 0. Well, if we plug in 0, f double prime is going to be positive. And if we plug in a value greater than 0, let's say 1, or sorry, not greater than 0, greater than 1/2, we are going to see that f double prime is going to be negative, because 1 times by negative 12 is going to be negative 12. 6 minus 12 is negative 6. So f double prime is negative, which tells us, so because the inflection point, or because 1/2 changes from positive or positive to negative, or negative to positive, there is an inflection point at 1/2. So you have to plug this into our original function here, and that is a very mess, so we're going to use a calculator for it, and that comes out to be 1.5. So we say that there is a inflection point at 1/2, or 0.5, 1.5. Well, we also, from our wonderful little diagram here, also know where f is concave up or f is concave down. So f is concave up from negative infinity to negative 1, or sorry, not negative 1, 1/2. And f is concave down from 1/2 to infinity. You may have noticed that I am not including the endpoints here. And that's just dealing with proper math notation. We do not include endpoints whenever it comes to concavity. Alright, so now we have to do what is called the second derivative test. So suppose f is a continuous function near c. If f prime of c is equal to 0 and f double prime of c is greater than 0, then f has a minimum at c. If f prime is equal to 0 and f double prime of c is less than 0, I suppose I forgot the 0, then f has a maximum at c. So we want to use this to determine the relative extrema of the following function using the second derivative test. Well, we have to start by taking the derivative, d over dx. So we get f prime of x is equal to, well, the derivative of the first, which is 2x, times by the natural log of x, plus the derivative, plus the first times by the derivative of the second, which is 1 over x. So we get f prime of x is equal to, we're going to factor out an x from this. So we get x times by 2 natural log of x plus 1. We are then going to now, we are now going to designate these as possible critical points or critical numbers. So we have x is equal to 0 because we have this x on the outside. However, we also have to deal with this 2 natural log of x plus 1 on the inside, so we're going to solve that for 0. 0. So we have 2 natural log of x is equal to 1. Then we have to divide both sides by 2, so we get 1 over 2 is equal to the natural log of x. So we have to just exponentiate both sides, so we get e to the 1/2 as our answer, or for our second critical number. Now we have to do a bit more of a challenging part. We are going to take these two critical values into the second derivative and plug them in. I need to make that look a bit more like a 0. So the second derivative of x, in this case, is going to be equal to 2x times by the natural log, or sorry, not 2x, but 2 times by the natural log of x times by the first, which is just plus 2x, times by the derivative of the second, which is 1 over x. But 1 over x and the x kill each other off, so we get f double prime of x is equal to 2 times by the natural log of x plus 1. Alright, now we can plug in values into this function, so we get f double prime of 0 is equal to 2 times by the natural log of 0. The natural log of 0 here is undefined. Alright. Now let's try plugging in e to the power of 1/2 is equal to 2. Alright, natural log of e to the 1/2 plus 1. F double prime of e to the 1/2. Well, the e and the 1/2 will cancel, so we're left with 1/2 plus 1, which gives us 3/2. So we're going to get an answer of 3, which is positive. So there must be a minimum at at e to the 1/2, comma, and now we have to plug this e to the 1/2 in here. E to the 1/2 squared is e times by 1/2, so that's going to be 1/2 e to the 1/2. Alright. However, we don't, because f double prime of 0 is undefined, the second derivative test is inconclusive. Alright, well that's all I have for you. I hope this video has helped with your understanding, and if not, feel free to leave me comments down below. Have a wonderful rest of your day.